Ladies and gentlemen, good evening. I'm Christos Panagiotou from PK New Technologies. PK New Technologies is a new established SME located in Patras and is mainly active on the ICT domain and particularly the Internet of Things and the cloud services. Healthcare services nowadays face several challenges, especially due to the pandemic and the constraints that introduces. Significant effort was given in reducing the hospitalization costs and delivering high-quality healthcare services in remote self-assisted environments. In that context, we organize today this session under the context of Health Forum, the 10th Health Forum, organized by Forum Υγείας. In that context, we will present the activities performed in the Plan V project, which deals with an online platform for speech and language therapy with virtual agent. On the second part on our session, similar efforts will be given and presented in the sector of the remote healthcare and assisted living environments. I would like to welcome Archonto Terzi, professor in the Department of Speech and Language Therapy in the University of Patras, to give the introduction to this session with a description of the Plan V project.
The thing is that I can't see. It's very far, and I don't see the...
Hello, everyone. As Christos said, my name is Archonto Terzi, and I am a professor of linguistics at the Department of Speech and Language Therapy of the University of Patras. So I'll give you an overview of what this project is about from a linguist or language person point of view. I'm not an engineer, but a language person. First of all, this is a project that involves 3 labs, two university labs and 1 research center, Athena, and 2 private companies, PK and a clinic. So it brings together engineers, clinicians, linguists, and speech-language pathologists. Why are we doing this? We are doing this, I have to be very slow. We are doing this because we want to promote the effective support of people with neurogenic communication disorders, people who had some language problem, who have some language problem, which they acquired when they were adults, from a stroke or something like this. And why? Because they need intensive and continuous systematic intervention for their language, which is scarce. The resources available are usually not sufficient, and the way our health systems go, they will be less and less sufficient. Nevertheless, they need support. And then, because it has been already reported from similar platforms in other languages that this way of therapy, this type of intervention through a platform, through a computer, through a tablet, is efficient. It works. But we cannot, I mean, we can transfer the technology, but we cannot transfer language. I mean, we cannot take Italian and implement it to Greek, so we have to do something for Greek. What did we do? First of all, I can't, yeah. I'm not sure. Yes. Once more. Oh, yes. Yes. Okay, I found it. So, what does this platform target? It targets speech problems and language problems. What are speech problems? The manner in which we talk. We may say nonsense, or we may say magnificent things, but sometimes we either don't breathe very well, or we don't pronounce some sounds very well, and we have to correct this. And we also have language. Language has words, and words make sentences. And there are people who don't do well on this either. They may have a wonderful way of articulating what they say, but they cannot they cannot put words together, or they misinterpret words, and or they make sentences that they are not good, and so on and so forth. So we target two domains of language, speech and language, of the system, of the linguistic system, speech and language. What do we do for speech? I'll give you an example. The example we have here is yes, yet why? But why? If someone can do this for me, I would be very happy. No. Matching task, auditory, no. I need to find the previous video. If someone can find it, yes. So this, you think, I can't possibly do it. Can we play the video from here, you mean? Maybe you try. If you can go and, yeah. So this is a video that shows how we train people how to breathe. Αν πας εκεί κοντά. Αλλά πρέπει να πας, εσύ μπορεί να πας κάτω. Well, there are lots of videos, and the fun part of it are the videos, though, so it's unfortunate. So what we do there is have a video that plays how the person breathes and how long they should or they can hold their breath, and how much they should prolong their breath, so that they are trained to speak, to breathe well, to breathe properly. This is a necessary step in order to continue with other steps, because most people who have this type of problems, elderly people, they cannot breathe properly for a number of reasons. So this is a breath exercise. When we go to language exercises, as I said before, actually, yeah, it's not only breathing that we do, we also do, in the domain of speech, we also do things like how to stress a word, to say Maria instead of Maria, or to distinguish between άνοιξε η πόρτα and άνοιξε η πόρτα. The first one is statement, the second one is a question. People have to be trained to do this, because sometimes the way they stress their voice does not make any difference for the sentence, for the meaning of the sentence. And sometimes you mean kalos and kalos are two different words. So you have to learn to stress them properly. And some people cannot do that. So this is another step in the domain of speech. We continue now with a few things about language. As I said before, language involves words and sentences. When it comes to words, we can imagine, actually we have two types of exercises, which unfortunately cannot be shown here, and we target two aspects of the words. sometimes people cannot start a word. They have to, you show them a picture, let's say, yeah. We cannot play the videos. This is a very beautiful video with a cat and a number of animals. So they show the picture and they hear the word cat. The picture has the video has a lot of pictures, like 7 or 5, depending on the level of difficulty. They hear the word cat and they have to point to the right picture. If they don't, we help them. And there are 2 ways to help them. Either to tell them if they pick up a wrong picture, either to tell them some characteristics of that animal in this particular case, or let's say, for instance, if they choose the dog, it means they have a semantic problem, which is a problem with meanings. They get the category of things, but they cannot target the precise animal. So what do we say when they give us a dog instead of a cat? We say, well, try again. You, the animal you are looking for likes to eat fish. Another kind of help we can give is to tell them, try again. The word we're looking for starts with the gata. Another type of similar word training exercise is an exercise again which targets semantic features. What is, again, there are features that have to do with the meaning of the sentence. So again, we give them a cat. And they will identify the cat. If they don't, we help them. And we ask them things. There are a number of properties around them. And we, like, for instance, what does it eat? Is it omnivorous? Is it carnivorous? Is it vegetarian? And they have to pick up the right answer. There are lots of little questions like this that have to do with the characteristics of the animal. In this case, there are not only animals, there are lots of other pictures like professions, like fruits, like vegetables, like parts of the body. And they have to be able to tell them. They have to be able to identify features of the meaning of these words. So we do that. The platform does that. Starting from the, continuing to, we started with words and we continue with the sentences. Words build sentences. And there are people who cannot build sentences. So they are really, the sentences are fragmented, like yes, no, doctor say yesterday. They have to learn how to build a sentence. We start with assessing how much they know. Let's say we have on the left side a picture that shows the one I had here was the doctor is in the left picture. Look here. Peter is watching the doctor who is examining the lady. And in the other, so they have to identify the picture first, because in one of them, it's the doctor who is examining the lady, in the other, there is the lady that is examining the doctor, which is absurd, but it has to be there, because we ask such types of sentences as well, so that we make sure they understand, because if they see a doctor and a woman and a lady, usually they would choose what we expect them to choose. If they don't choose right, if they choose right, we have them produce a sentence like this, saying something like, in this picture, you see, in the left picture, Peter sees the doctor who's examining the lady. In the right picture, what do you see? And they have to say, in the right picture, Peter is seeing a lady who's examining the doctor. These are not simple things. I mean, this type of sentences, which are called relative sentences, are difficult. They're particularly difficult. So we train them because, not only them, this is a good example, though it's unfortunate you can't see the pictures because it took a lot of effort to make them. So they have to construct them. If they cannot construct them, we help them to construct them. And Kostas very well knows how we're supposed to implement this. We start with the first sentence, Peter is seen, and then you say, now we connect the sentence with the other one. The lady, the doctor is examining the lady, and then you have you put them together, but then it's not enough. They have to construct the whole sentence. And there's a number of very, very delicate and detailed steps that the platform follows, which you can see, in order for them to build the sentences. So I know I will take like 2 more minutes because, so I talked a little bit about breathing and stress of the words and things like this that are called speech. And I said a few things about language, namely vocabulary, lexicon, and sentences. So this is it. But it's an enormous amount of material. I mean, it's a lot. And no speech pathology in their home can ever have this material to give it to the patients. And the thing is, what do you do with the speech pathology? So do they lose their job? No, they don't lose their job. Well, they are the ones, they will be the ones who will assign the exercises to the patients. They will assign them according to level of difficulty, actually, or according to what is the weak point of the patient, because this is assessed too. If they have a phonological problem or if they have a semantic problem, remember the words have both phonology, how they sound, but also meaning, what their meaning is related to and stuff. And then we have sentences, which is another thing. So according to what their weak domain is, speech pathologists will assign them the exercises. They will exercise at their own space, at their own time. I remember my mom had to do things like, not language, but some other psychological, whatever exercises, and she wasn't always eager to do them when the person came at home. Here, with this platform, they can do them whenever they want. And then the speech pathologist can see the results because the platform knows the results and see where they're doing good, where they're doing bad, and they can continue assigning or reassigning more or fewer, etc., exercises. So this is the idea. It's very unfortunate that we couldn't show the videos because this is the whole clue of it. It's very good for me because I couldn't see very far anyway, so, but I can describe. Yes, and I'm done. Yeah.
Thank you very much, Professor Tezi, for giving us these insights on the background of speech and language therapy in the context of the PLARVI project. Now I would like to give the floor to Dr. Evi Faliaga, Research Associate of the Embedded System Design and Application Laboratory of University of Peloponnese, to give us the technological advances in the context of the PLARVI project.
Hello, I am Evi Faliaga. I am a postdoc researcher in the Electrical and Computer Engineering Department of the University of Peloponnese. And today I will present you how to integrate speech therapy platforms with ambient-assisted living environments. Modern technology platforms and speech therapy platforms specifically have a crucial role in many areas of everyday life and have applications in various fields. Ambient-assisted living environments need such platforms to support their residents. Patients can practice on their own, in their own environment, without the physical presence of the clinicians, while clinicians can monitor, assess, and evaluate the progress of their patients. Our goal is to provide an easy and an as automatic as possible integration of speech therapy platforms with ambient-assisted living environments. AAL environments have some specific features that must be taken into consideration in order to make a successful integration. First of all, they have a lot of sensors to monitor the vital signs of their residents, so we have to manage with heterogeneous data. Second, the data we have to manage is private information, as there is the medical and personal information of the patients. Also, there is no guaranteed quality of service of internet access. And last but not least, the majority of the patients have low familiarity with internet technology. Here we can see the architecture of our system. As you can see, the architecture is composed by 3 levels. The first level is the main infrastructure that we have built, and it is called Atlas. It consists of 3 main subsystems: the storage subsystem, the user management subsystem, and the database subsystem. All 3 subsystems are based on microservices so as to easily be adapted in new platforms. The second level has the integrated components, and here we can see that there is the Plan V platform, and here we can adjust any other new platform that uses the subsystems of Atlas. Finally, we have the user interfaces, that is the forms that patients and therapists use to communicate. Except from these 3 layers, we have also a data aggregator that collects all data from different sources, filters them, or even makes the appropriate calculations and forwards to the appropriate component. In our case, we have used this API so as to communicate with ILSP and exchange the information needed for the avatar. Now I will present in more detail these subsystems. The file management subsystem can support all available types of files, images, videos, and audio files, and it is implemented using Minion, which is an open-source distributed storage server. It is designed for cloud computing infrastructure, and it's suitable for storing unstructured data. This is the data that we have, like photos, videos, logs, backups, and containers. When we have an online system that manages such sensitive data as the medical and personal data of patients, we have to ensure the security of this data, and also we have to secure the privacy of the patients. Also, in this project, we needed some roles with different privileges, so we have implemented the roles of the patients, the speech therapists, and the speech therapy centers. The database subsystem can supports all types of databases, both relational and non-relational, even time series databases. In our case, we have used the relational PostgreSQL database, and here you can see a snapshot of the database schema that we have implemented. The information of the main entities, users, patients, and exercises are stored in the tables shown in yellow. The results of the exercises are stored in the tables shown in green, and all other information that is related to the files, that is the paths, the file names, are stored in the tables shown in red. All of these subsystems are implemented on Docker technology using microservices, as we want to be scalable and easily adjust to the requirements of new platforms and towards the sustainability of the project. Here you can see the main microservices that were implemented in the Plan V project. Finally, we have the graphical interfaces. Our system can support all types of modern technologies for creating interfaces. In our case, we have used React.js, which is a JavaScript library for creating graphical web interfaces, and also we have implemented additional modules for state management, routing, and API interaction. Thank you very much.
Thank you, Dr. Falyaga, for this very interesting presentation on the technological background of the Plan V project. But another core component of the Plan V platform is the processing part of the speech and language of the patients. In that part, the Athena Research Center, represented by Spiritoulas Stamouli and Manos Plitsis, will give us the details and the insights. Please.
Good evening. Thank you for our presence here, and I'm going to share my screen now and the audio. So let me can you see our presentation?
Not yet.
We are in a screen sharing mode.
Okay.
Is it okay now?
Yes, yes. The floor is yours.
So I am Spiritoulas Stamouli, and a research associate of the ILSP Institute for Language and Speech Processing of the Athena Research Center, and my colleague Manos Plitsis, who is a computer scientist. And we're going to present our research tasks in the context of the Plan V project regarding speech and language technologies, which are in line with the major aims of the project, which were mentioned by Archondo Terzi, focusing on the second and the third aim, which is to assist speech and language pathologists in the design and remote administration of individualized intervention plans, to assist patients in their remote sessions, and to reduce SLT's time and effort for the initial of their patients' impairment, for monitoring their patients' progress, and for evaluating intervention outcomes. So with respect to the objective of assisting clinicians in the initial assessment of their patient's condition, we are developing an automated system for the initial assessment of aphasia severity and for monitoring patients' progress. Our focus is on aphasia because it is one of the most complex types of neurogenic speech and language disorders, which affects both comprehension and production, at different language levels and at different degrees of severity. Our second aim is to assess language production at the word level and at sentence level in the context of name tasks and sentence production tasks. And finally, to guide the patients in their remote sessions with a virtual assistant. Regarding our first objective, which is the development of the automated classification system of aphasia severity, this slide presents the pipeline of this task, beginning with patients recruitment, who are people with aphasia of at least 3 months post-onset with no cognitive impairment, continuing with patients' assessment for aphasia type and severity. And following that, data are being collected either in person or remotely with the use of a web-based application. And we continue with data transcription. We are going to present this procedure in a while. Data are being collected by trained speech and language pathologists from the collaborating clinic, the Animus Rehabilitation Center, from people with aphasia, who are with different types and degrees of aphasia severity, as well as from healthy controls. Type and severity of aphasia is assessed with the standardized version, Greek version of the BDAE protocol, which is well known to speech and language therapists. And then each patient acquires a label for aphasia type and severity, which corresponds to the aphasia quotient score. So a person with aphasia can be labeled as one of these 4 labels: mild aphasia, moderate, severe, or very severe. Our data are speech production data of the narrative discourse type. So our patients are producing stories using a web-based application which integrates 4 tasks for discourse elicitation, for narrative discourse elicitation, 4 of which are adopted from the Aphasia Bank protocol. Aphasia Bank is the largest international repository of speech production data from people with aphasia. Let us show this web-based application. So all tasks are integrated within this web-based application. Instructions can be
Πείτε μου τι συνέβη όταν πάθατε το εγκεφαλικό. Πείτε μου τι συνέβη όταν πάθατε το εγκεφαλικό.
And all equipment is integrated in this web environment. So the user has just to press this button and submit the recording. And the following task will appear. This one is a narrative production task based on a 6-picture series. Recordings are being stored per participant task and session. And after this procedure, the speech samples are being transcribed and annotated following the specific format of the Aphasia Bank database, the chat format. Also, the speech data are manually transcribed and time aligned and segmented into utterances. This work is being done using this software of processing of speech production data.
Έβλεπα ένα παιδάκι.
Here you can see the transcription
Κλαίει.
as well as the audio time. Malini. Okay, so there are specific conventions for pauses or false starts, etc. It should be noted that all data, transcripts and speech samples will be contributed to Aphasia Bank as protocol data from Greek-speaking people with aphasia. Transcripts are automatically processed with natural language processing tools, which involve tokenization, lemmatization, parts of speech tagging, and syntactic parsing, in order to calculate several linguistic features, such as the ones shown, mean length of utterance, propositional density, words per minute, verbs per utterance, etc., which represent language ability at different aphasia severity levels. So Manos will now present the more technical aspect of the aphasia severity classification task.
Okay, I will try not to be too technical. So this is a diagram of the system that assesses the severity of aphasia in a patient. The input is a recording of the patient's voice. And we see that in parallel, there are two things that are being computed. The first one is the top one. The recording goes through an automatic speech recognition system, which automatically transcribes it into text. And then this text is used to extract these linguistic features that Pepe was showed earlier. So these linguistic features come from the content of the speech. And they show important aspects of the grammaticality, together with the timestamps produced show us how quickly the patient speaks. In parallel, the raw signal of the audio goes through another feature extractor that produces acoustic features. These have to do with the patient's style of speaking, and it doesn't have to do with the content at all. So the volume, the way of speaking, things like that are computed. These features are then combined, and they pass through a system that is trained to assess aphasia severity, and it gives us an answer as to at which severity level is the patient. Mild, moderate, severe, or very severe. So the problem we are facing to implement the system is that training these machine learning models requires immense amounts of data, which are very hard to obtain, especially for languages such as Greek. So our initial goal is to find a way to utilize data in other languages where we have more of it, like English, to improve the model's performance in Greek. So we're using automatic speech recognition to eliminate the use for human annotation. We are utilizing English data from Aphasia Bank, which is the largest database for aphasia, for aphasic speech. And then at the end, we will use a few Greek data to fine-tune and test the model. This work was presented last month in the Interspeech conference. We used English language data, and we just extracted the linguistic features that are common in all languages and trained a classifier that just detects the presence or not of aphasia in the patient for any language. It was trained on English, and then it can detect in any language like Greek or French. These results were satisfactory, so we are using this as a base to develop a system that also assesses the aphasia severity. Now, another technology that is used in the PLAN-V project is phonological error detection or evaluation. When patients are doing the exercises that Mr. Z described, it would be nice if the system could evaluate them in some way. So what we did is we trained the speech recognition models that when a patient pronounces a target word, they transcribe it, and then they calculate a Levenstein distance between the target word and the pronounced word, and in this way calculate a score. And we also created a data set of common phonological errors by working with speech and language pathologists who provided us with rules for these errors. And this will be used to test our phonological error detection system. And the last technology that was used is the assistant, the avatar, that will guide the patients through the exercises. I will first show you a sample.
Προσπαθήστε να παράγετε παρατεταμένο πρώτα με το στόμα σας μισάνοιχτο μέχρι η γραμμή να προχωρήσει από τη μία άκρη της οθόνης στην άλλη. Θα είναι ενεργοποιημένη η κάμερα ώστε να βλέπετε το στόμα σας. Πατήστε το κουμπί συνέχεια.
So this is a sample. It's an ongoing work, so it has been improved somewhat. The voice here is recorded. It's a female voice, as you may have noticed. It will be a male voice in the final application. The last thing I will talk about a bit is how we produced this avatar. This is we used this work by a team working for Adobe, the corporation. This paper is called Make It Talk, and it's a technology that allows a still image to be animated, to speak. So how this happens, you need an audio clip and an image, and this system animates the image and produces the result visually. So this, to achieve this, they used neural networks. There are many components of the system, so I won't go into detail, but basically landmarks are produced for a face, which can be either a photograph or a sketch. And then, based on speech, this model learns how to produce more landmarks to have a whole video of the face speaking. A problem that we faced was that these models were trained in English with a lot of data, which we lack in Greek right now. But it's working pretty well, and we're improving. And I think this is it for me.
Thank you very much. Thank you very much for giving us those insights on the intelligence behind the Plan V virtual agent. Now I would like to give the floor to Ms. Mariana Fragaki, the director of Animus SA, a rehabilitation center in Greece, to give us her view from the stakeholder approach. Ms. Fragaki, the floor is yours.
Good afternoon to all. Good afternoon, dear colleagues. From Animus, Larissa. I'm just waiting to see my presentation. Has to do with the internet speed. Yeah. Can you see it? I can see it in my computer.
Yes, we can see your presentation now.
Good. Let's proceed. My presentation is about the implementation, application of Plan V protocol in patients with brain injury in our rehabilitation center. Go forward. Wait a minute.
Is there any problem with your presentation?
It doesn't go forward. It may have to do with the internet. Just a patient. I suppose it will be resolved. Should I stop sharing and try again? No. That is. Can you see the next slide? Yes, suppose. Let's see. I will proceed. Animus started operating in May 2008 and is located in an exceptional area just a few kilometers outside Larissa in central Greece. Is it okay now?
No, we have lost your presentation again. Okay, now.
Yeah.
Please proceed.
Well, Animus, as I said, started operating in May 2008 and is located in an exceptional area a few kilometers outside Larissa in central Greece. The multidisciplinary rehabilitation team with more than 200 health professionals, fully trained, combined with innovative therapeutic equipment and modern facilities, ensures that the physical, emotional, and social rehabilitation of patients after an accident or illness resulting in serious injuries is the best possible, either as inpatient or outpatient. Animus is participating in a Plan V project by implementing, applying the protocols that have been agreed and created in Plan V in patients with brain injury, traumatic or non-traumatic, in order to collect variable data that will be used for the development of an integrated technological assisted speech-language intervention platform for people with chronic neurogenic communication disorders. The patients that are included should fulfill specific and strict criteria. First, aphasia. They should have aphasia due to brain injury or lesion. They should be over 18 years old, monolingual. The time passed from the disease onset is 4 to 6 months, and the neurological lesion must be located in the left hemisphere of the brain. Hearing and vision should be functional with no disorder. Patients with serious cognitive deficits and a mental state examination score lower than 18, with previous linguistic disorders or history of depression or other psychiatric disorders were excluded. The procedure involved, first of all, assessment of cognitive functions using tools like the mini mental state examination, RAVEN, and neuropsychological assessment with scales such as the geriatric depression scale. Narration data were collected by using pictures and repetition of small stories in order to collect data regarding the spontaneous speech by direct recording of storytelling in a specific soundproof room with the best sound analysis in our PC. Speech data were collected also by using the Boston Diagnostic Face Examination, of course, with 5 tests of Western Aphasia Battery Revised and Boston Naming Test integrated, in order to have as much data collected regarding comprehension, repetition, naming, and fluency, with our final goal being the definition as better as possible of the type and severity of aphasia. Additional data were collected regarding the production and comprehension of verbs and sentences using the Northwestern assessment of verbs and sentences tool, which was found difficult even for typical normal persons participating in the project. So far, our group of patients includes 17 patients, 10 male and 7 female, who fulfilled the inclusion criteria and completed the procedure, which is quite time consuming for the therapists, but most importantly for the patients, who find it sometimes very difficult to complete all the tasks and takes a lot of hours of sessions to complete all the scales and the tests that are needed. We have a limited number of participants so far due to the strict inclusion criteria, and also something that was not a fact when all this was planned. The great limitations due to COVID-19 pandemic. For example, we had many problems with the participations of patients, especially in the first year, because they hesitated to participate. We had very strict rules regarding the isolation of patients, especially the inpatients, and the allocation of therapists. All data that are and will be collected will be reassessed and processed again before the final analysis. Thank you for your attention, and I'm at your disposal for any questions or clarifications, if I can answer, give. Thank you.
Thank you very much, Ms. Fragaki, for your presentation. Now we have closed with the first part of our session. That was the main parts of the Plan V project, an online platform for speech and language therapy with a virtual agent, funded by the national funds from the General Secretariat of Research in Greece. Now we'll proceed with the second part of our session, where we have colleagues from other organizations and entities in Greece and other countries of Europe as well, to give us some insights on their activities and advances regarding the remote healthcare and assisted living environments. I would like to ask Mr. Dr. Ioannis Hadjigiannakis, professor at Sapienza University of Rome, to give us his presentation and his views on this domain.
Hello, thank you for the invitation and the very interesting presentations. Well, the project, the work that I will present is not connected to speech technologies. Rather, it is connected to blood glucose level for type 1 diabetes patients. Here I will present a collaboration we had with the University of Murcia and the Polytechnic University of Cartagena. The goal is to understand the benefit of big data when we are trying to predict the blood glucose levels. So essentially, we are discussing here about type 1 diabetes people, where this autoimmune disease destroys the insulin-producing cells in the pancreas. So these patients need to inject the hormone exogenously or wear an insulin pump. And of course, predicting the level of glucose is extremely important for them to understand the levels of insulin that they have to inject. So here we are using a system that is comprised of different sensors. The main element is the continuous glucose sensing. This is a device that goes under the skin and allows us to measure the frequency of about every minute or every 5 minutes, depending on the manufacturer, the level of blood glucose. And then, of course, given some analysis of the data, also in combination with other sensors, decide the level of insulin that should be injected. So here we have this view of the artificial pancreas. The idea is that we have the different sensors that are attached to the body of the patient, then using a local personal area network, these data are collected, they are analyzed, and then of course they are transmitted, the decision is transmitted to this pump that is injecting the insulin to the body of the patient, or if there is no such pump available, of course, we provide feedback to the patient so that they can inject by themselves the proper amounts of insulin and the appropriate insulin type. At the same time, information can be transmitted to the cloud so that we can have remote access by healthcare personnel, or we can have a re-evaluation of the data and the readjustment of the software and the algorithms by combining different data coming from different patients. So this is something that needs to be done at the local level. And of course, we are dealing with different kinds of personal data. As you can see here in this plot, we have heart rate, the exercise of the patient. Then, of course, we have input connected to the blood pressure, to the temperature, the meals, and so on. And of course, the question is, all this data, how can they contribute to an accurate short-term prediction? This is an example plot of a patient where we can see the periods where it's resting, or it is having some exercises throughout the day in the working environment, or in the afternoon due to sports and so on. We can see the level of glucose, the different meals recorded, and so on. So this is just an example. And our question, of course, is what is the utility of all this data in this specific problem that we are addressing? So until now, the approach followed by the majority of the projects and the platforms proposed in the relevant literature was to collect as much data as possible. And this could potentially help patients and, of course, physicians to adjust the therapy. Of course, now we understand that this volume of data is overwhelming, and of course is creating serious problems in dealing with this and understanding how they fit into an accurate forecast. So in this presentation, I want to focus on some questions connected to the actual volume of data that can help us. But of course, similar questions are valid for the variety of sensors or the velocity of the data. So these are essentially the main dimensions for that constitute the big data domain. So here we start by trying to identify the minimum kind of variety. So we evaluate single sensor values, of course, starting from the blood glucose levels, and then adding here additional sensors. Then we want to examine the accuracy of the prediction models based on this volume by reducing, that is, the number of data points, the number of samples. And we would like also to examine the velocity of data. So I mentioned earlier that data are arriving also at 1 sample per minute, but we could reduce this velocity to 1 sample every 5 minutes or every quarter of an hour and so on. And of course, minimizing this is extremely important when we are dealing with a wearable device, where the computational resources are not unlimited, like, let's say, in a cloud environment. Or when processing is carried out remotely, of course, we want to minimize the level of data that are transmitted to the cloud. Clearly, here there are also issues connected to the privacy. By reducing all these dimensions, of course, we are limiting, let's say, the exposure of personal data in case of a breach, or in general, the need to store all this data at a cloud level. So for this study, we have a detailed passive monitoring campaign, which involves 25 patients of type 1 diabetes, and they were enrolled at the University of Murcia under the endocrinology department. Each patient was provided with a wearable device from Abbott. Essentially, this is a CGM system, and they were given also a mobile application to log their meals, a Fitbit control wearable device to log their activities. All these were connected to the Android phone. The specific glucose sensor was using an NFC connector. The Fitbit device was using Bluetooth, and then data were transmitting to the cloud. So there was a combination of protocols, and this was done for a period of 9 days that created this comprehensive data. You can see here the clinical characteristics of our cohorts. So more or less, these are well-trained patients. They have been into the diabetes for a fairly long period of time. We see here a median of 24.5 years. And generally speaking, of 9 years, it's their age of about 25 years old. And in general, there are people that are of normal weight. So here we can see the first technique that we tried. This is the autoregressive integrated moving average, ARIMA technique. It is a well-used technique in the bibliography. We can see here the different prediction horizons in terms of minutes. So in the first 15 minutes on the x-axis, we see the prediction after 15 minutes, 30 minutes, 45 and 60, so an hour after the last measurement was acquired from the sensor. And then on the 5 different plots, we see here the window of previous values. In case we have 3 hours of data, 6 hours, half a day, a full day, and then up to a day and a half. Now on the y-axis, we can see the root mean square error of the prediction of the expected glucose level. And we can see here, interestingly, that by increasing the past values, essentially the improvement is minimal, quite the opposite. We see that the longer we go, the larger the number of data we provide to the algorithm, the error increases. Slightly, but still it increases. Of course, for all cases examined, a prediction of an hour, of course, has a bigger error than that of just 15 minutes or half an hour. While the computational efforts for executing this algorithm, we can see that significantly increases. So while predicting the glucose level using only the last 3 hours requires about 26 to 28 seconds, when we increase the volume of data, of course, the computational effort increases as well. Here, the processor that we are used is an ARM Cortex used by Raspberry Pi version 3. So this is a processor comparable to those that we have in, let's say, common mobile phones. We followed the same approach with other techniques like random forests. I'm going to pass very fast the results, and also SVM. So these are well-known techniques from the literature. We are not using any neural networks here. We decided to use simple approaches that can be easily implemented in a mobile environment or in a wearable solution. So overall, we can see here that with essentially only one type of data, we can achieve a very good performance. Of course, we can improve this performance by introducing additional sensors that can reduce further this average error, which, however, is already low enough for this kind of diabetes type 1 patients. Interestingly, if we reduce the velocity of the data to one reading every 15 minutes, again, the error is within the accepted margins. It is, of course, increasing, but still it is acceptable. So essentially, here, our analysis indicates that we can provide very good results, even when we are not collecting really large volumes of data. And of course, we would like to extend, and we are currently extending this study in longer prediction horizons, so in 4 or 6 hours, and whether this observation holds, or also consider other diabetic patients of type 2, where, of course, the condition is not exactly the same, but there is some kind of insulin production, but at much lower levels. So with this, I would like to conclude. And of course, I'm available for any kind of questions or comments regarding this issue. Thank you. Thank you for your attention.
Thank you very much, Professor Hadjigiannakis. You gave us a very good example of how technological advances can contribute towards predicting and preventing critical health issues, and that something that finally reflects to the overall quality of life of patients. Thank you again. Now I would like to introduce Dr. Ioannis Giallelis from University of Patras to give us his perspectives and activities on the assisted healthcare. Please. Yes.
Good afternoon to everybody. My name is Ioannis Giallelis, and I'm from the Applied Electronics Laboratory from the Department of Electrical and Computer Engineering in the University of Patras. My presentation has to do with the biosensor systems utilized in emergency departments and hospital clinics for the priority triage and monitoring of medical events. And this is a presentation that has to do mainly with wearable systems which are utilized for the priority triage. This project is a project that it was in the framework of research, create and innovate of 2017, 2021. 2021, 2017, 2021. And it has to do with the development of design and development of the total system of a total trial system in which an important matter is the wearable systems and how they affect the quality of the triage. So my presentation is focused mainly on wearable systems and not with the whole system in general. So let me go ahead. Okay. In general, this one is the correct one. What is portable wearable devices in general? Well, they are electronic devices of small size, equipped with powerful microprocessors, efficient microcontrollers. They do have a variety of standard interfaces for connected specialized sensors, such as temperature sensors, accelerometers, optical sensors, and biometric sensors. They have a power management mechanism for long autonomous operation, which, as you can understand, the longest the better for the patients and in general for the users. They do have wired and wireless interfaces, standard interfaces, adequate local memory, and of course, they are placed in or near the body and are able to sense the person wearing them and their surroundings. So wearable devices include any device that can be worn by humans, such as wrist watches, helmets, patches, shoes, glasses, lenses, hearing aids, armbands, chest straps, rings, prosthetic sockets, smart clothing, textiles, and so on. All these wearable devices belong to the Internet of Medical Things, together with the implantable, ambient, and stationary devices that we can find in a hospital. The number of globally connected wearable devices is about to reach 1 billion, and this is a measurement that I got from the German company that specializes in market and consumer data. And their use is becoming very increasingly widespread, and they are talking about, an estimation is about approximately 33 billion in 2019, and is expected to expand at high rates in the next few years. And this is according to the consulting company market research and consulting company, which is based in the United States, India and the United States. And these devices, what they do, they monitor and facilitate people's lifestyles. They allow data exchange via the internet with operators and or other connected devices. The range of application is potentially unlimited: health, sports, industry, robotics, etc. And the capabilities include biosignal collection, processing, storage, transmission, bioparameters extraction, information display, status activity assessment, personal alerts, updates, contact communication, localization, feedback and activation, delivery services, and so on. Well, although here is something that we have to notice is that although the readings are not yet as accurate as stationary devices in hospitals, which is a very hot research topic, they are sometimes considered acceptable depending on the application. Here is the wearable devices application model. You can see here the wearable devices belong to the, I would say, on-device computing. Then we have the edge for or fog for computing, and then we have the cloud computing. Well, as you can see this here, in the hospitals, the middle layer, the edge fog computing, actually is something that we have to avoid if we want these devices to operate properly in this domain. Continuing the smart assistants, here, yes, okay. Now we go to the other category of the wearable devices, which is the medical wearable devices. What are these? Mainly are smart assistants that support doctors. They manage data streams for the patients, evaluate emergency in a timely manner, react immediately and make decisions, handle the timely administration of medication, carry out timely stimulation of vital organs, and the effective healthcare, they affect healthcare as they reduce waiting times, reduce time to response, reduce errors, improve organization and planning processes, increase patient and employee satisfaction, and finally, they can increase revenue. They are vital since they can detect life-threatening conditions, collect biometric data to help diagnose diseases, supervise the administration of medication, and of course they collect data. The vast amount of data they collect are useful not only for consumers to manage their health, but also for the healthcare organizations to improve their facilities and services. The data are analyzed by clinicians and other health professionals in order to provide accurate diagnosis, advice on treatment, detect health emergencies, monitor patient compliance, assist, and of course they assist in research. Here I have put some numerous well-known signals and signs that are read from human body to identify vital signs and other information about the health or mental state of the subject, and they are including, I'll go fast on that, EDA, ECG, PPG, EOG, EEG, and all these nice words here, EMG and EGG. Mainly this is the same thing as where we can go and get those signals from a human. And here is the healthcare tasks and sensors that are used for that. So to go fast from that and show you a few medical devices, medical certified devices that are used right now in the hospitals. This is a wearable device that they called it Wavelet, which is the measurements that you can get from that is heart rate variability, oxygen saturation, respiratory rate, and activity assessment. Another one is this smart cardia. They can estimate heart rate based on ECG, heart rate based on PPG, heart rate variability, SpO2, skin temperature, perfusion index, and of course they can assess the activity and posture of the body. The vital patch is actually gets the ECG, the electrocardiogram. They also measure skin temperature and they estimate heart rate, posture of the body, variability, heart rate variability, fall detection, respiration rate, and activity. This is something that you put on this place of the body, as you can see there. It's not a wrist wearable device. Some others, the Check Me Pro device, it's a very convenient device, and it can measure through the electrocardiogram, the ECG or the PPG, the heart rate, the oxygen saturation, the body temperature, and the Bluetooth. They have Bluetooth connectivity. Another one is CareTech Medical. Another one is a live core cardia module, which mainly, as you can see, they can measure. They are able to measure the caretaker medical is blood pressure. Can measure blood pressure, heart rate, and they have Bluetooth connectivity. Okay, this one, there is another device, it's from a Chinese firm called Berry. This one we have used, it's very accurate and lasts and with long autonomy. You can have a heartbeat, heart rate actually, oxygen saturation, and they have a connectivity, Bluetooth connectivity. Okay, what was this few words about the project that we were involved? The main thing, the aim was, the objective of the project was to implement a wearable device which will have all these good, as I said, advantages of the wearable device, but it could be easily interconnected to the infrastructure, to the existing infrastructure of the hospital. Our job was to make a device to connect to the Wi-Fi infrastructure of the hospital and to have at least 48 hours of autonomy, transmit real-time heart rate, blood oxygen saturation, and respiratory rate, and at the same time make coffee. No, this is a joke. But in general, it would also detect the location of the patient, since this device did not only utilized for the triage, but also afterwards, if the patient was hospitalized, it should follow all the cycle of the hospitalization of the user. Anyway, so such a device was designed and developed by our laboratory, and with, I would say, most of the requirements that were put in the beginning from the project, and actually the end user, which was the hospital, the emergency department actually of the hospital, were met. Now we are in the process of certifying this device, which is a long process, I would say, since it has to meet a lot of standardized procedures, etc. So thank you very much for your patience. I'll be available for questions, etc. Okay? Thank you.
Thank you, Dr. Yalelis. Thank you. Very good presentation on how all these multidisciplinary sensors could be integrated and perform data fusion to operate in remote environments. Now I would like to ask from Oscar Zanuto representing the Institute for Hospitalization Services and Assistance to the Elderly, to give us his perspective on remote healthcare and technological advances. Please.
Thank you. Hi, everybody. Thanks a lot for having us in this invitation, in this important forum. A few words about us, and then I go to the presentation. So we are a public care provider based in Italy, in Treviso, in Veneto region, in the northern east part, just nearby Venice, but maybe you know better. And I'm in charge of European department that you see, that is this one, that is European factory, that is the unit belonging to this public body. So let me share my screen and presenting this project, that is Value Care project, that is in Horizon project. We started a couple of years ago, and it's important to say where we started from. So this project was a call regarding the digital transformation, and it's about the value-based methodology for integrated care supported by ICT. It means that our starting point was how it could be possible to translate the Michael Porter, who is an American economist, who in 2006 discovered the idea that if we keep going in delivering, let's say, performances in a quantitative way, we cannot change the clinical outcomes. Instead of this, we need to move towards a outcome-driven care. So now if I can move the slide, we are frozen a bit. Let me check. So yeah, the consortia is about 17 partners, so from 8 countries. The leader is the Erasmus Medical Center in Rotterdam. There are also other Greek partners, the Athens Medical Group and Vidavo, who is a company working on technology, and the other come from, let's say, both 8 countries with several kind of skills. I skip this one, and I move to the core concept of Michael Porter, that is how we can deliver value. So integration is in the core of the process, and integration is almost a challenge in between social and health worlds, but sometimes they are, let's say, far away from each other in terms of interoperability of data and the exchange of information in a, let's say, easily mannered and way that could support people. So this model started in US, but is almost based on private insurance, as we know. And so, let's say, this reimbursement system pushed the market in, let's say, putting together the players. But now here in our project in Europe, we have to find a European way to translate those concepts, moving from what is called competition for results towards cooperation for results. In this project, we are using the ICHM set questionnaires, so because it's crucial, it's value-based to utilize the PROMs, that is the patient report measurement, and the PREMs, that are the patient reporting experiences. We are using this set of outcomes evaluation to do what? To measuring the creation of value, that is the ratio in between the outcome patient experience and clinical results divided by the cost, direct and indirect, that we are willing to provide. So the question could be where technology is in this situation. So mainly, once we put together as much as we can in the pilots, and we will have 7 pilots. We have 7 pilots because we started just a couple of months ago. We are using a chatbot that works as virtual coach that will foster and present the integrated care plan to each person, touching several dimensions. The ones on the left are the physical activities, the mindful concentration, other kind of movement exercise, and my network, la mia rete. So how I can expand my social connections. So we have been working a lot as psychologists, and this is almost our knowledge, in building the contents of the speech dialogue interaction, that is the ones that you see here, what I have the arrow. And the person set the number of exercises and the frequency that should be at least 4 times a week for 3 weeks, but usually they do more. And in our case, we are considering the mild cognitive impairment disease. So our focus is about this. And also we support this using a smartwatch that do a lot of things that colleagues before me told. So we can use those functionalities, but mainly because of our interest is to improve physical activities. So we track this, so movements, but also the sleep quality, because there's a huge correlation between, let's say, bad sleep quality and initial cognitive decline. We are using a dashboard for this backend dashboard for practitioners, but they set the goals and they overlook the graphics along the time. And so the 3 points of connection are dashboard, smartwatch, and the application. Those are the 3 components in terms of technology that we are delivering. In terms of pilots, we have both 7 in Rotterdam about stroke. In Cork and Kerry is about integration between services for frail people. In Coimbra is social isolation and frailty. In Valencia, it's a mixture of, let's say, cognitive decline and social isolation. In Rijeka, in Croatia, it's about heart failure and, let's say, cardiovascular disease. And in Athens, it's about type 2 diabetes and in Treviso MCI, as I said. We are now approaching the inclusion and treatment groups with 120 persons, and we will have 120 as control groups, but also, and this is important in the value-based healthcare model perspective, we are also engaging in between 50 up to 70 caregivers, 30 up to 40 healthcare professionals and managers, because also in terms of business model and the exploitation part of the project, for sure, this management part is quite relevant. So if you want to stay tuned and follow what is going on in value care, you can find us in Twitter, and yeah, there's also an email. So this is what we would like to share with you all, and thanks once more for PK and all the organizer of this very interesting events. Thank you.
Thank you very much. It is clear from your presentation as well that virtual agents and coaches attract significant interest in modern remote healthcare setups. Now I would like to ask from Mr. Dimitrios Amaxilatis to give us Sparkworks' view on remote healthcare and assisted living.
So, thank you very much, Christos. Good evening from my side as well. Okay. So I'm Dimitris Maxilatis. I'm the CTO of Sparkworks. It's a technological company with more than 10 years in experience with e-health, Internet of Things, and smart cities deployments. We work both on research projects and also in development effort. We are a certified AWS partner, and we have received the Amazon Well-Architected Review in products that we have both in hardware, software, and integration applications. And I'm here to talk today about the Smart Work project, a project that targets helping and aiding older workers in staying safe and active in their workplaces at the later stages of their careers. And the tools that we developed in this project that is now concluded as of this summer help them, as I say, stay longer in their workplaces, be safe, learn new skills and familiarize themselves with technology. And it helps also transfer the knowledge from them to their younger colleagues so that we have a smoother transition to the new generation. And also provides tools to monitor their chronic health conditions that are more common in such older ages. So in the project, we developed solutions that are both hardware-related, software-related, and on the application side, and use new technologies like machine learning and AI to do so. So the project has a total of 10 partners. Also from Greece, we have also BITE and the University of Patras. And in order to achieve all that we want as part of Smart Work, we have a network of unobtrusive sensing around each worker participating in the project. And we use for that a set of devices that can monitor different physiological and environmental characteristics in their workplaces. So we have an intelligent mouse that the workers use while interacting with their computers in order to estimate their mental state and their composure during their work hours. We also use activity trackers like the ones shown before in order to monitor their physical activity both during their working hours and off work in order to understand how their life goes on after work. We also use devices like smart scales and sleep trackers in order to understand how the conditions that they are experiencing in their workplace can affect them at their lives outside of work. And we also complement these with environmental sensing devices like the environmental sensor box that Sparkworks develops in order to understand the surroundings of the workers and how the conditions at their workplaces affect their conditions or not. And finally, for personalized health condition monitoring, we also have integrations with a wearable ECG device that we are also developing as Sparkworks, and we can also integrate with devices like the ones showed before, like glucose meters and other specialized hardware, depending on each case that we face. And in order to glue all these devices together, we have developed a set of applications like the HealthyMe web and mobile application that are used for visualizing the data collected from the users and interacting with them in a more easy to understand way, as they are also older people that are not so familiar with technology. So we can send them notifications, updates, or suggestions about how to improve their lives. And from these applications, we can also share with them training and exercising material about developing how they can develop new skills and how they can develop new competencies for their work, and also, let's say, adapt to a more healthy lifestyle at the extent that they can, of course. And finally, there are work-related applications that can assist them in communicating and collaborating with their partners at work and their colleagues. So, for example, in this slide, we can see how we can show a worker an exercise about helping them with their back. There's some information about what they are going to achieve with this, and how they can perform the exercise with a video that gives them this guidance. And this is an overview of how all this is glued together. We have on the left-hand side of the slide all the hardware, the devices, the smart devices, and the wearables that are in the system. All these communicate either through the worker's smartphone or their work computer that collects the data, and this communicates with the cloud infrastructure of smart work that is based on the Sparks IoT platform for integrating all the data and fusing them together. And this is provided later on to applications and services that work on the back end or on the front end in order to extract knowledge from the data collected and provide feedback to the users and to the caretakers as well. So to evaluate the whole system, there were two trial periods of 3 and 6 months respectively. They were tested in two large organizations. One is in Portugal, Caritas de Coimbra, and also in Denmark in the municipality of Aarhus. A total of 121 employees participated in the trials, and we monitored these workers during their office hours in their workplaces, and at some parts also while they were at home. And the system was able to produce, using artificial intelligence, assisting notifications for the users and alerts about how they can improve their everyday lives. So the interventions that were produced by the system were either short-term goals, like I want to move today a bit more than yesterday, long-term goals, I want to adapt to a more healthy eating lifestyle, let's say, or personal goals like reducing my weight or becoming more productive in the morning hours of my work. And also notifications about what they did wrong or what they did correctly in their past days. And this also was complemented by challenges between the workers and rewards in the system as they achieved their goals every day. So regarding the age of the cohort that participated in the trials, we can see here that we targeted workers that were above 55 years old. Most of them were around 60 or 65, let's say, and we also had some people that were even older than that. And in this slide, we can also see how two of the indexes that we monitored were improved after the completion of the trials, like, for example, the sleep quality index of the users that improved, let's say, by a level after the trials, and also the workability index that was slightly improved as well after the completion of the 6-month period. Of course, these results are not so much, let's say, so good as we expected, but we understand from that this needs to be applied in much longer periods in order to get a better result from this. But this shows how things start to improve after adapting these tools. So that was from my side. Thank you. If you have any questions.
Thank you very much, Dr. Amaxilatis. It was a great presentation to close the series of technical presentations. Now I would like to ask from Giorgos Koumanakos from Frontida Zois to give us his view as representing the end users and the stakeholders of such applications.
Good evening from my side as well. As Christos said, I'm going to speak on behalf of the caregivers and say a few things regarding technologies, who they are coming and they are very valuable as a helpful tool for the caregivers. So I represent Frontizo here in Patras located. Is a non-governmental organization taking care of older people, and lately we have a dementia care center for care of dementia patients as well. I would like to start with the essence of well-being in old age. It's not different, of course, than the essence of well-being for all of us. We try to have the best possible living conditions, but in old age, in older ages, we have also the aggravated factor of the inevitable biological decline, which is something that makes things worse, and it is something that older people have to cope with. And I will say from this point of view, the meaning of the well-being is, of course, connected with the quality of life, but it is also an answer to a simple question of how well a caregiver will say, how well a person in his everyday routine manages his reality in social, personal, health context. So what we need successful interventions. And these interventions, they have to cover all the matrix, all the context. So we need interventions for the physical, for the emotional, for the social, for the cognitive function as well. What interventions should focus above all is to improve and promote what we said before about the quality of life of older people. If they do this for us as caregivers, they are successful interventions per se. Sometimes, not sometimes, many times though, we have to do adaptations. We are speaking for older people, and we are speaking for, as we said before, compromises in terms of physical or mental or any other category of an older person's daily routine. So in this, from this point of view, we have to adjust, and a good way to adjust, a strategy, a good strategy, a sound strategy for us to adjust is to use three techniques. The one is to select what the older person can do better and to stick to this and to insist on this. The second one is to compensate, to replace some losses with some things that the older person can use in order to achieve an everyday goal or a more long-term goal. And the third one is the optimization, which is to maximize the resources an older person has. But in order for these interventions to be successful, we need quality. And by quality, I will summarize, there are many issues. I will summarize that we need a skilled workforce, and as technology goes on, and as new things coming to help caregivers. We are not speaking merely for the basic health knowledge or care-related knowledge, but we speak about skills concerning the whole spectrum of health, social, and lately ICT and artificial intelligence and assistant technology skills. Another important aspect and context and category for the quality, for the interventions to be qualitative is the attentiveness in care. We need, as caregivers, to attune to a person's need, to adjust, and of course, to treat an older person with affection and empathy. And of course, self-management and shared management, this is a very delicate balance between what the older person can do and what we can help him or her to do. This is a delicate balance and also is a vital as a knowledge for a caregiver to know, especially after the coming, as I said before, the upcoming of the technology. So far, as from DISO, we have certain interventions. We have our daycare center. We have home interventions through a mobile unit we have training seminars, a lot of them, sporadically, and whenever we have new carers to train or to update the knowledge, and we have several actions, activities in order to raise awareness. And of course, online interventions as well. Our team is very active in this field. But apart from our interventions, we are now coming to the era of having the help of technology-based interventions, and this is also something that is close to the subject of this seminar. We know that technology can help us in a lot of issues, smart home technologies, early detection of diseases, management of diseases, maintenance of social connections, reducing social isolation, smart homes, all these things you know very well. And the benefits of the technology, if I could say from the part of caregivers, they are not different from what many research tries are stipulating, but from our point of view, I could mention some of them which are salient in terms of the effect they have on an older person's life as it is right now. So we have socialization and inclusion, which is, I would say, probably the most important aspect and characteristic in order for an older person to be confident, to be cooperative, to have self-esteem, to have self-confidence, which is very important. We have aging in place. I would say that asking an older person, he most probably will answer that he would love and he would like very much to have the opportunity to age in his place among his own familiar persons and his own environment. Facilitating the work of caregivers. Caregivers are people who they are aggravated apart from the tasks they have to do with their personal problems, issues, reality, and for many of them, taking care of an older person is a complex issue, is a risk situation. So having the help of the technology in diagnosis, more personalized treatment,
tailored health management accompanied by numbers and data, valuable data, effective monitoring is very, very important. Lessening the burden from the caregivers is connected with the previous one, but it is more expanded here because apart from the security of having a help is also very important, the opportunity for the caregivers to lessen their burden, to get lessened by their burden, to feel more relaxed, to give time and to dedicate time to their own personal life, to feel more comfortable. All these things are, we can base on the technology as well. Lack of caregivers, this is not a characteristic, this is a fact. And here again, technology can prove to be very important because we have lack of caregivers, either formal or informal, and technology cannot substitute, in my opinion, this lack, at least completely, but can contribute into dampening this lack and this subsequent effect of the lack of caregivers. Healthcare recommendations, again, connected with the work of the caregivers, and here technology can give us very important help in terms of prevention and of having the opportunity to save things before they escalate, and also in the decision and in the treatment as well. And here it is very important because technology can provide accurate and precise and up-to-date and more complex, of course, data, which are very helpful, not only for the caregivers, but for the clinicians as well. Here, we speak about technology in the broader sense of smart homes, of assisted living environments. We are also, as caregivers, getting to know them, getting familiar, and we know that they can promote the independent living, they can promote autonomy, and this is very important for an older person and his family. Excuse me. And lately, it is the robots. We are also getting familiar to them. We are getting acquainted with their possibilities and capabilities and capacities. This is a work that is in progress, but I'm sure, we are all sure, I suppose, that in the coming years, humanoid or not, for companion or not, robots are going to take a part, a substantial part probably, of the caregiving tasks. And finally, I would like to speak about challenges from the point of view of caregivers. Here we have the digital literacy. We know that many people that are coming, younger, older, as we say, they are more familiar, but we are not speaking only about the literacy of those that they do not have a knowledge, but we are speaking also about the literacy of all of us, because technology is continuously creating new knowledge requirements by, how can I say, by rebirthing itself. We have the over-reliance or misuse of technology. Those are very important risks in terms of not from the one point over-relying in technology and having an older person more passive than active, which is important. And also misuse of technology in terms of safety, in terms of data protection for these issues. And the reasons mainly, we have communication and human contact. Here, we have to be aware that technology might substitute actions and services, that it should never substitute the human contact. And we know that social inclusion and socialization requires technology, even with this form from distance, but this is a danger, an existing risk that human contact should not diminish. And cost and accessibility, I will say here with a simple words that for caregivers, technological innovations and technological tools are valid only and to the point that they can be massively used and be massively accessible. I think this is all. I will say that right now we are, as Frondizo, participating, and that's how our knowledge comes from technology in different European projects. One, the current one, is about health literacy and e-health literacy through digital health literacy, which is a very challenging task because digital health literacy not only requires digital literacy, but also requires other medical connected knowledge. And in this point, in this direction, we have also another project which is called Resil for Care, and is connected with what I said before about adaptation and resilience of caregivers in order to be effective in their tasks with the technology. We have to be adaptive and resilient. Thank you.
Thank you very much, Mr. Koumanakos and Frodida. It becomes crystal clear that as the needs for remote healthcare environments and assisted living setups rises, the incorporation of cutting-edge technologies will become imperative. I would like to thank everyone, the participants, the presenters, and wish you a good night. Thank you.